Hello guys, welcome to Backbencher Studies channel. I am Umesh Kumar. Now today we are going to learn the basics of how to solve a signal flow graph using this Mason's gain formula. So how we do that, we will be looking at how to solving at the determinant of the signal flow graph and the determinant of this isolated path and how we do that, and based on the determinants and forward path gains we will be finding out the overall transfer function of the system. So how we do that we'll be discussing in this tutorial or in this lecture. So let us start our session. So here we have this signal flow graph which was being given with corresponding gains. This is being the input R, and this gain is 1, and this gain is G1 is given, G2 1 is given, and G3 and so on. Like this is the signal flow graph. So moving on for the step 1, we have we have to find how many forward gains are there, how many forward paths are there. Remember, the forward path is nothing but a node or a path traversing in the direction of the arrow from input node to the output node. So we have only one path seeming as per the directions, direction of the arrows given. That is this straight line being given. So we have one path, forward path gain, that is the product of individual gains of these branches. We have G1, G2, G3, and G4 we have. So that is being discussed over here. So we have this forward path gain that is being depicted over here. And moving on to step 2, we have to find out how many loops are there in the signal flow graph. We have 4 loops that is being uh, depicted. So we can see this loop that is being covering these two branches, that is G1 and -1. So thereby giving us the loop gain of the first loop is minus G1. And similarly, we can say the loop gain of the second loop minus G2, minus G3 and minus G4. We have 4 loops that are being written over here in step 2, and we have to find out the determinant of this isolated path. So what we do here is del 1, that is the first path that is being forward path, that is being recognized as forward path. We have to take out all the nodes belonging to forward path. So if we take all the nodes which are in this forward path, we left with no signal path, no signal flow graph over here, because this forward path containing all of the nodes which are being in the entire signal flow graph. So we can have all the loops are vanished. So we thereby we have, what is this determinant? If we take out this forward path gain, how many loops will be there, and their loops summation would be here, and plus non-touching loops will be there. So this is the isolated determinant. So here in this particular example, if we take out all of these forward path nodes which are being in the path P1, then we are left with nothing. We are left with no loops. So this del 1 can be written as 1 minus 0. So thereby giving us del 1 equal to 1 over here in this corresponding. So here, this is how our diagram will look if we remove all the nodes involved in this forward path P1. So we don't have any loops, we can observe. So thereby giving us this determinant 1. uh, I hope you have understood this isolated forward path. And if we moving on to next step, we have the total determinant of this signal flow graph, which can be depicted using that Masson-Gay's formula as 1 minus sum of individual loops plus sum of product of non-touching loops. So we have, if we see this, we have loops which are, we have individual loops which are 4 of loop gains L1 and L2 and L3 and L4, and we have two pairs of non-touching loops, one being 1 and 4. So this one loop and fourth loop are also, these two are non-touching loops, and 2 and 3 are non-touching loops. So thereby, what are non-touching loops? We have already discussed. So the nodes which are containing a common node are called non-touching loops, and if we don't have any common node or something, then that is non-touching loops. So we have a non-touching loops pair. Based on that, we have written this product of two non-touching loops L1 and L3 and L2 and L4. So if we substitute these values, the gains of these loops corresponding, and using Mason's gain formula P1 del 1 by delta, we can have this transfer function which is being given over here. So this is how we can kind of solve the signal flow graph using Mason's gain formula. Thank you guys, and in the next video we'll be discussing another problems and another type of problems which are given in GATE. So thank you guys, thank you. If you do like my explanation, please share this channel, and please do like and please do subscribe to our channel. Thank you guys.